Welcome back, junior geometry detectives. I'm so glad you're here for today's explainer, where we're going to investigate architectural blueprints to uncover the secrets of the trapezoid. I am beyond excited to have you join me as my lead investigators. Today, we aren't just going to sit around and memorize math rules. No way. We're going to carefully inspect the evidence, decode structural diagrams, and figure out exactly how this incredible shape works. So make sure your magnifying glasses are polished and your detective notebooks are ready to go.
Here is our investigation dossier for today. We're going to look at the trapezoid blueprint, discover the median, unlock the area formula, check out the suspect lineup, investigate the isosceles upgrade, and finish up with a final detective challenge. Let's get right to it. All right, Section 1, the trapezoid blueprint. Let's look at the anatomy of our subject.
Okay, so we're starting our investigation by looking at the raw structural anatomy. Take a really close look at this blueprint. What jumps out at you right away? Well, look right in the middle at those thick red arrows pointing to the right. You can kind of think of those arrows like railroad tracks. They're totally parallel, they stretch on, and they are absolutely never going to touch. But what do you think is going to happen if you look at those dashed lines forming the left and right sides? If you were to trace those upwards, they'd eventually crash right into each other at that red X at the very top. Because they crash, they are definitely not parallel. In geometry, we actually call this defining rule the prime directive. So why is this true? Well, if those crashing sides were actually parallel railroad tracks too, the shape would just become a closed loop, which we call a parallelogram. But a trapezoid, it strictly limits parallelism to exactly one pair of sides. So to summarize our very first clue, exactly one pair of parallel sides is literally what makes this shape a trapezoid. Now that we've got the prime directive down, let's label the rest of the evidence. Take a look at the top and bottom flat lines. Can you guess what we call those parallel top and bottom pieces? It's kind of like a house, right? Think of them as the floor and the ceiling of our structure. In math, we call these the bases, and they're labeled here as B1 and B2. Now, what about those non-parallel sides that lock the whole shape together? Well, those are called the legs. They're just the sides that enclose our structure. And finally, if you look down at the bottom corners where a base and a leg actually meet, you'll see these little green arcs. Those show us the base angles. You might be wondering, why do these names even matter? Because these specific parts are the exact building blocks that enclose the entire trapezoid perfectly. So to sum it up, bases give us the parallel floor and ceiling, while the legs and base angles build the walls.
Moving right along to Section 2, discovering the median. It's time to find the structural equator.
So how do we find the exact middle of our structure? Look really closely at the diagram here. What do you notice sitting directly on those slanted legs? Yep, there are two bright red dots. And do you see those little red tick marks just above and below them? Those tick marks actually mean that the dots are sitting at the exact halfway point of each leg. Imagine you're building a ladder, and you need to figure out exactly where to put that middle rung. When you connect those two midpoints straight across the shape, you reveal this really powerful mathematical line called the median. Why does it happen like this? Well, the median basically bridges the midpoints together, acting like a structural equator right through the absolute center of the trapezoid. So basically, the median is just the internal scaffolding that connects the exact middle of both legs.
Okay, before we even look at any math formulas, let's use our detective logic to figure out how long this median actually is. We know from our diagram that the median perfectly follows the prime directive, meaning it inherently locks into parallel alignment with both the top and bottom bases. So how do we measure it? Think about it for a second. It's perfectly halfway between the shorter top base and the longer bottom base. It's literally the average. So logically, our steps are super simple. Step 1, verify they're in parallel alignment. Step 2, add the lengths of the two bases together. And step 3, just cut that total in half to find the structural average. When you understand it like this, you realize you don't even need to memorize a complicated equation. The median is simply the exact average width of the top and bottom.
Which brings us to Section 3, unlocking the area formula. We're going to calculate the internal space. Our next clue requires us to measure the total area. That's all the space inside our shape. Look at that red dashed line, labeled with an H. Notice how it just drops straight down and hits the bottom base at a perfect 90-degree angle? Think of it like a sheer drop straight from the roof all the way down to the floor. We call this the perpendicular height. Now, here is where our entire investigation really comes together. To find the total internal space, we take that structural average we just discovered
the median, and we just multiply it by this sheer height. Why is this true? Well, the really elegant reality of the area formula is that if you average out those slanted walls, you essentially turn the shape into a simple rectangle of average width. To summarize, memorization really isn't needed when you see the logic. Area is simply the average width multiplied by the sheer perpendicular height.
Let's review the steps and see how this builds our formula piece by piece. First up, you calculate your median. That's your 1/2 times base 1 plus base 2. You're just finding the average. Second, you identify that straight perpendicular drop, which is your height. And finally, you just multiply that median by the height. It really is that simple. We're proving that area is just the average base multiplied by the sheer height. Beautiful detective work, everyone. All right, section 4, the trapezoid taxonomy. It's time for a suspect lineup.
Just like in any good investigation, not all trapezoids look exactly the same. So let's take a look at these 3 suspects side by side. Can you spot the differences? What do you notice about that very first one on the far left? Well, look at the green boxes in the corners. It's standing straight up with adjacent right 90-degree angles. We call this suspect the right trapezoid. Now look at the middle one. It looks totally chaotic, doesn't it? No equal angles, no equal sides whatsoever. This chaotic shape is known as the scalene trapezoid. Finally, look at the one on the far right. Notice those little red tick marks on the legs? That means the non-parallel sides are mathematically equal in length, giving us the isosceles trapezoid. You might ask, why does this taxonomy even matter? Because the lengths of those legs actually change everything about the internal angles. To summarize, right, scalene, and isosceles variants all follow that prime directive, but they definitely have distinct visual identities based entirely on their legs.
Now for section 5, the isosceles upgrade, we are looking at the absolute peak of symmetry. For the most critical part of our case today, we really need to zoom in on the most perfectly balanced suspect in our lineup. Take a look at that dashed line cutting straight down the middle. What happens when the legs are mathematically identical in length? It creates perfectly balanced mirror images on the left and right sides. We call this amazing revelation the isosceles upgrade. But why is it an upgrade? Because of this forced symmetry, the structure inherits some totally unique geometric properties that our chaotic friend, the scaling trapezoid, just doesn't have. So, in short, when the non-parallel legs are identical, it forces a structural symmetry that sets this shape strictly apart from all the others. Because of that perfect symmetry, some truly amazing things happen inside. What do you notice about the colored arcs in the corners here? The 2 bottom angles are both green, and the 2 upper angles are both orange. They mirror each other completely. We call this angle congruence. Why does this happen? Well, because the symmetrical legs tilt inward at the exact same rate. It forces the pair of base angles at the floor to be mathematically identical, and the upper angles at the ceiling to be exactly identical too. To summarize this first property, the symmetry literally guarantees that angles adjacent to the same base will always mirror each other perfectly.
Now, which internal lines look really special here? Check out those lines spanning from corner to corner, passing right through the red dot in the middle. Think of them kind of like internal cross braces on a massive steel bridge. We call these lines congruent diagonals. Why is this such a special property? Well, unlike a parallelogram, these cross braces don't necessarily cut each other perfectly in half, but their total span from one corner to the other is exactly identical in length. To sum it up, these identical internal cross braces lock the structural symmetry perfectly in place.
Okay, so this crucial point is neatly organized right here in our diagnostic matrix. Let's quickly review the evidence. All 3 suspects, scalene, right, and isosceles, follow our prime directive, meaning they all have exactly 1 pair of parallel sides. But notice how as the structural constraints tighten up, the geometric properties multiply. The right trapezoid adds those 90-degree angles. But the isosceles trapezoid, it represents the absolute peak of symmetry, giving us congruent legs, congruent base angles, and congruent diagonals. And that brings us to section 6, Detective Final Challenge. Let's test your blueprint knowledge. It is time for your final case review. Let's see if you can solve this interactive detective challenge. Question number 1. Which structural trait is the prime directive required for all trapezoids? Take a second to think about it. What is that one absolutely unbreakable rule that makes a trapezoid a trapezoid? If you guessed exactly 1 pair of parallel sides, excellent detective work. Remember, if it had 2 pairs, it would be a parallelogram. And those parallel sides? Yep, those are our bases.
All right, question number 2. Let's do a little bit of math together. If the top base 1 is 10 feet and the bottom base 2 is 20 feet, what is the length of the median? Think back to our structural average steps. What exactly do we do with 10 and 20? Have your guess ready.
The answer is 15 feet. And this brilliantly illustrates that the median is literally just the average of the two bases. You add 10 plus 20 to get 30 and simply cut it right in half to get 15. Incredible job! And now for our final mix challenge. Which specific trapezoid features congruent legs, congruent base angles, and congruent diagonals? Try to combine everything we just learned about perfect balance and symmetry and tell me which shape has all of these special properties. It's the isosceles trapezoid. You have successfully closed the case on the trapezoid blueprint today. Now, I have one final provocative thought to leave you with. True detectives don't just recognize the evidence, they can recreate it. So, I challenge you to grab a piece of paper, draw this isosceles blueprint completely from memory, and explain its properties out loud just like I did today to completely solidify your brilliant detective work. Keep investigating, and I'll see you in the next explainer.